Okay, hello. Um, Bonjour. That's what every foreigner says when they come here and say hi. So I can't be the odd one out. But thanks for being here. Thanks for having me at Hack in Paris 2016. It's my first time. I came to Paris as an exchange student a few years ago, but I've never actually been here since I started working. But today I'm going to be talking about making and breaking machine learning anomaly detectors in real life. So there's a slight difference from the title you see in your program, and that's because I'll be focusing not only on how to use machine learning for your security applications for anomaly detection, but also on the vulnerabilities that come with using machine learning as a web application firewall or any kind of security detection system that might be applicable to you. So. Just have a show of hands here. How many of you guys are engineers or hackers who have played with machine learning before? Okay, so that's quite a good number. So today what I'll be mainly doing is to give an overview of machine learning anomaly detection, to spark discussion on when, where, and how to create these and how to use this in a security context, and explore how safe these systems are. And then we can discuss where to go from here. The goal is not to tell you like what to implement or to give a very deep dive technical into the statistics behind all of this, because there are so many resources online for that. But my research is mainly focused around using this in security and what concerns there might be. So something interesting that I decided to do this year was there's the RSA conference held in San Francisco every year in February. And every year, companies from the Bay Area, companies from Silicon Valley around the world, they'll go and have booths there. And companies, they'll have descriptions of what they do. So walking around RSA, I always feel a little bit puzzled because all the companies seem to describe themselves in the same way. They use the same words. And this is a particular interesting one that I highlighted. Deep Instinct. I'm sorry if anyone is from Deep Instinct here, but I just like the fact that they call themselves the first company to use deep learning to do cybersecurity. But anyway, what I did was to just do a simple study on the company descriptions. And companies that use machine learning, deep learning, AI, or big data adaptive, the number of companies that have been doing that since 2012 to 2016 has been steadily going up, especially between 2013 and 2014. I'm not sure the reason why. I'm sure you guys have noticed as well. Between 2015 and 2016, there's a slight drop, maybe because people start feeling that it's becoming a little bit too, too much of a buzzword and not real anymore. But there certainly is industry interest in this. So let's just define some things. What is machine learning and what is anomaly detection? So traditionally, WAFs, web application firewalls, WAFs have been heuristics or rule-based. And I'll have some examples of how you would use WAFs today, traditionally, to define rules for when you want to start blocking a particular IP address or a particular attacker to your servers. Machine learning is the opposite of heuristic or rule-based, or at least that's the idea. Because if you have a rule that, let's say, you want to start blocking an IP address when it makes 100 requests per second to your server, you want to prevent your server from being overloaded or DDoSed, then you can use, then the attackers will just start doing it 99 times a second and start to expand the number of IPs they use. It's so cheap these days. But for machine learning, the idea is that these rules are fuzzy. So there is some elasticity in the rules that are used for these systems, and they can start to learn when hackers are trying to avert your detection. So the intersection of machine learning and anomaly detection can be, in this presentation, we'll call it outlier detection or predictive machine learning. We will try to predict when attackers are going to do something weird to try to avert your detection by rules, and that's the whole premise of this. So some interesting applications of machine learning in the security industry or in security applications today. The very famous one, of course, Gmail, about a decade ago, they started introducing spam detection systems. And this was just using simple Bayesian statistical models to find out the probability that an email is spam when it comes into your inbox so they can classify it properly. I don't know about you, but when I started using Gmail when I was younger, I really felt the difference between Hotmail and Gmail. So this example in particular is very interesting because there's no actual words, but Gmail is still somehow able to find that this is spam and it's not something relevant to what you might want to see in your inbox. You see, credit card fraud detection also uses machine learning. This is very common nowadays, and it works very well. Botnet detection, it works for detecting the CNC endpoints in particular botnets for compromised machines, and also just standard server anomaly detection, looking at the traffic coming into your server aggregated by IP addresses. So all these are fine. They're very established uses of machine learning. But let's say you're a sysadmin or you're an engineer in a particular company and you were tasked with trying to come up with a way to prevent DDoS attacks or the high load on your servers because you suspect that someone is trying to attack you. You look at server logs, HTTP Apache server logs, and just, how do you find anomalies in these? It's just not very clear. Traditionally, WAFs have rule engines like this. So for example, if the user agent matches a particular string, request methods get, and the source IP is this particular IP address, which you see has been making 10 requests per second for the past few weeks, then you start to block it. So this is all very simple and easy to understand. So why is this good? It's easy to reason about. It's simple and understandable. It can also be dynamic and adaptive in the sense that if you have a human in the loop, if you have someone who is there constantly monitoring the traffic, then you can react quickly to changes in the attacker's patterns. And you can see, so there must be a security expert in the loop, someone who understands your traffic patterns, and it makes it easy to update these rules. But why are machine learning techniques attractive compared to the traditional way? Number one, it's adaptive. You don't necessarily need to have a security expert in the loop. Let's say you deal with a huge number of endpoints, you deal with a large amount of traffic, and your website is so complicated that it's just hard for any one security person or team to even deal with the amounts of traffic that comes in. Machine learning offers the promise of being able to learn the patterns of traffic in the normal state and then detect when something abnormal is going on and then try to trigger alerts so that you only bring a human into the loop when you suspect something. So for the people who have implemented machine learning in their security applications before, those people who raised their hands up earlier in the room, I suspect a very common way that you start doing things is through Python scikit-learn. These are just some very simple examples that I got online for how you might do classification of traffic. And similar to this, an example of how this might work would be if you get HTTP traffic in your logs, and then you start to classify individual requests and map them out onto some kind of kernel. And this kernel would be able to define a decision boundary in which you would classify as normal if it's inside the decision boundary and abnormal if it's outside. Then if traffic comes in that maps to anywhere outside your decision boundary, then you would basically classify it as abnormal and maybe block it, maybe send it to a CAPTCHA page, or maybe send it to some other page to verify that they're not automated traffic. But obviously, the reason I'm here is not to tell you about why machine learning is so great. There's already a lot of material out there that does that. It's not a silver bullet. If you remember the slide earlier where I showed a lot of companies are starting to use machine learning as a marketing term, I think a lot of people in the security industry tend to think that machine learning is this black box that can solve a lot of problems. But obviously, it's not, and there are problems with it because it was not designed for use in a security context. There are a lot of problems with regard to robustness, and especially in the field of adversarial machine learning, it is susceptible to attacks. So some successful ML applications that are very suited for the machine learning problem are product classification, product recommender systems. Amazon.com is one of the most popular online retailers in the US. And when you buy something, when you browse something, if your Amazon search history contains some kind of term that's roughly related to gardening material, then they'll start to bug you over the next few weeks and months with gardening material that you can perhaps buy. So as I mentioned earlier, simple Bayesian systems can also determine if an email is trying to market you some kind of enhancement products. Something pretty interesting that I have seen in the past is also using deep learning or semantic systems to understand language. This example in particular is pretty interesting because language in itself is a complex thing to really program out, and the heuristics of which are very complicated. So looking at this sentence, this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. As a traditional, naively implemented semantic analyzer using not machine learning techniques might look at the words clever, intelligent, and humor and just think, okay, these words are all very positive. Maybe it's a positive statement. But the doesn't word in front there, it just negates everything. So because there are so many different kinds of exceptions in language, and I don't know French, but I'm sure that there's small exceptions like these all over the language as well. And so if you were to program something different for each one of these rules, you have the different exception for each one of these special semantic quirks, then this would make the program pretty intractable. So what this does is basically a deep learning system that reads languages, that reads in large blocks of text, and then starts to learn whether this is positive or negative based on labeled training examples that you give it. And you don't have to explicitly do feature engineering because it's a deep neural network, and it can purport to give you good performance when you are dealing with complex language structure. So, of course, we have to set expectations. The first part of this presentation will be focused on how you might use machine learning in your security applications and how you might evaluate it. In the second part is the core of my research this past year, and I'll be dealing with basically how you attack these systems and how successful I have been in attacking systems like this. So the big ML anomaly detection problem is that if you go search online on Google Scholar, on academic papers on using machine learning in anomaly detection, using machine learning for statistical outlier detection, there is a lot of research. However, if you look at actual solutions being used in the wild today, the most common ways to do outlier detection is still not based on machine learning. And why is that? I have done a lot of reading into this area, and I realized that there is one main thing that seems to be the problem. So traditional machine learning is about learning patterns. If, let's say, you have two kinds of images of apples and oranges, and you wanted to teach this machine to identify if this image contains an apple or an orange, then the machine would basically be fed in with examples, labeled examples of whether this image is an apple or an orange. You feed it 1 million images, and then a new unseen image would basically be classified according to the features that this machine has learned. Anomaly detection, however, is a whole different class of problem. It might seem similar at first glance, but then when you think about the complications around this problem, you're actually trying to find novel attacks. You're trying to teach a machine to understand things that it has never seen before. And you want it to alert you when something it's never seen before comes up. So these are two different classes of problems, and statistically, there are a lot of interesting theorems around why they're not the same and why you cannot just use standard classifiers to do anomaly detection, even though there's a lot of companies that promise to do things like that. Okay, so what makes anomaly detection different from other problems? I've identified 5 here, and I'll be going through each one of them in the following few slides. So compared to other learning applications, there's a very high cost of error. So if, let's say, you have a recommender system, let's say you ran Amazon's recommender system engine, and you just recommended someone a rake after he was searching for a gardening hose. The person may not be in the market for a rake or other gardening material, but you recommend him that, and there's no big loss there. It's just some maybe potential business loss that you might have, but you don't lose a customer per se. It doesn't harm the whole user experience. However, if you ran an anomaly detection system that was protecting the front end of your website, and a request comes into your site that somehow matches to one of your machine learned heuristics that thinks that this person is actually an attacker, when in fact he's not. Maybe he's just using Wi-Fi from a Starbucks that happens to have had a lot of attack traffic in the past, or he's using some kind of proxy that makes his traffic more suspicious. Then he's blocked, and it's really a big harm to the user experience of your site, and you might start losing users if you do that a lot. Also, the false negative rate. If, let's say, you have sysadmins that are in charge of looking at alerts that this system brings up, and there is a lot of false positive when the machine learning is too relaxed. So let's say it starts flagging a lot of non-attack traffic as attacks, and the sysadmins will slowly start getting more tolerant to these alerts, and then they'll start to ignore them. And if there are any false negatives in there that are not caught, then it's also hard to verify whether there's actually any attack traffic in there or not. So lack of training data is a big problem. Which data to train your model on? It's hard to clean the input data, because if you could gather perfect, clean data in the first place, then you must have had some kind of human or enough labor or a perfect enough system to label this traffic. A lot of the time, it is unclear whether the traffic that enters your web server is real or not, or is human or not. So a lot of labor has to be put into gathering the training data that is relevant for training your data set. It is also hard to interpret the results in alerts. Let's say you have the rule that we saw earlier. If any alert is triggered, it is very clear what caused the alert and which IP address or which user account is being compromised or is attacking. However, if you have a machine learning system, if you are using some kind of adaptive model, then it is more complex how you explain why an alert was triggered, because the model is constantly adapting. If you're using online learning, then it's also hard to keep track of when the alert was triggered versus which model you're using to trigger the alert. And lastly, I think the more serious one is the evaluation problem. Devising a sound evaluation scheme is even more difficult than building the system itself, because let's say if you had an oracle that was able to tell you how effective this particular system is, then you don't really need the machine learning system in the first place, just use the oracle. So the problem with relying on anomaly detection and machine learning in evaluation in academic research papers is also interesting. If you look at a lot of research papers that are dealing with machine learning and anomaly detection, they're using data sets from the 1980s, from the Department of Defense in the US, and all these data sets are not exactly representative of what you would see in a modern web server today or any kind of modern internet traffic. And lastly, adversarial impact. So advanced actors can and will spend the time and effort to bypass your system, especially in the context of security. No one is going to try to bypass a recommender system by Amazon, because there's no payoff in that, at least no payoff that I can think of. But there's a very direct and there is a very high payoff to bypassing any kind of anomaly detection system, malware classifiers. If you can trick the system into thinking that this piece of software or this particular PDF doesn't contain malware, then you have successfully perpetuated your goal, and you have successfully spread this piece of malware. If you can trick the system into thinking that your attack traffic isn't really attack traffic, but it looks like human traffic, and the system lets you through, then you have succeeded. So how have real-world anomaly detection systems failed? There are just too many false positives. There are case studies of people using machine learning in anomaly detection, and the problem of sysadmins or security ops personnel receiving too many alerts is very real. It's very hard to find attack-free training data, as I mentioned earlier, and it's used without deep understanding often. There is a lot of understanding in the machine learning community and artificial intelligence community, but in other parallel fields, it just seems like people are using libraries without really understanding why a particular Gaussian kernel is used, or why a particular method for feature engineering is used, or feature or dimensionality reduction. So hopefully, by talking about all of these concerns, I can help to spread some knowledge about why you should do evaluation of your systems properly and choose systems that are more robust in the implementation of your applications. So is it hopeless? Obviously not. I think I'll be going into how you build a system like this and how it can be attacked. So first of all, the toy problem here that we have is that you run a web server. A very common task, I'd say it's 70 to 80% of the tasks out there that use anomaly detection systems. You have to generate a time series from this web server data that you're collecting, whichever kind of data, most commonly web logs. And you can generate one or multiple time series. It could be the number of times this IP address has visited your server. It could be the periodicity between this IP address visiting our server. It could be the user agent in particular that is visiting our servers. There are so many attack tools out there that help users that help botnet operators or attackers mask their traffic that look like human users by launching different browsers, making different get or post requests with different user agents, even going deeper down into the stack and changing what kind of browser plugins are available, what kind of system fonts available, because all these are techniques that traditional web application firewalls use to detect if this particular attacker is making multiple requests or not. Then you have to select representative features. And by doing this, what I mean is that when you look at a weblog, you have to manually generate features that are relevant to your problem, and then you can map them into a statistical space and perform statistical analysis on it, which is what machine learning is. Then you have to train and tune the model to the notion of normality and alert if incoming data points deviate from the model. So this is what I was talking about earlier when you have points on a graph in 2D space as shown earlier, and then you plot a decision boundary, and anything inside the decision boundary is normal. Anything outside, you alert. So common techniques for learning and classification are density-based models. You can use support vector machines, neural networks, correlation-based, or clustering. All of these they're all very interesting models, but I won't be going to them because you can read about them on a textbook or online, or you can just take the Coursera machine learning course and everything will be covered. What I'll be focusing on today is clustering because it's the most visual, it's the most easy to explain and bring across. When you have clustering, it means that when you map a particular event or data point into a particular dimensional space, in this case, it's just a simple 2D space. You have the x and y axis. When your points map onto this feature space, there will be clusters of points that hopefully will form. And each of these particular clusters have some kind of similarity measurement between them according to the x and y features that you have defined. And once you have determined a centroid of clusters, then anything that lies outside of these clusters within a certain threshold of your error prediction, then anything that falls outside of this will be basically defined as anomalies. This is good for online learning because there are a lot of algorithms out there that deal with distributed clustering, that deal with message passing between clusters, and you can very easily kick out old points that have been in your system for a longer time so your system doesn't grow exponentially over time. How do you select features? It often ends up being the most challenging piece of the problem because the success of your machine learning model depends on the features that you select. I think methods such as principal component analysis, PCA, or deep neural networks have been so successful because they extract the human out of the problem. When you're dealing with dimensionality reduction with a human expert in the loop, then you would be looking at basically brainstorming or looking through different possibilities or features that you can implement that makes your model successful. But because of the difficulty of evaluation and also the difficulty of coming up with good enough features to make your model more accurate, to make your model more efficient, then this is obviously a very difficult problem. So what PCA, what deep neural nets do is they help you do dimensionality reduction without understanding anything about the model at all. And they also help you to do machine learning without any kind of manual feature engineering. But isn't it just a parameter optimization problem, you might think? So if you had 1,000 features and you want to find the most important features, let's say the most important 2 features that can help to map your data points, your events onto an x and y axis for you to do clustering, then can't you just choose different permutations of these features and then just find the one that gives you the best problem? So it's difficult because there is too many combinations to iterate over. It's hard to evaluate in the first place, and there's a frequently changing optimal. Let's say you run a web server, and then there are different notions of normality over time. Web servers don't see very stable traffic. If, let's say, your website sees more traffic today, is it because there is a botnet trying to attack you, or if maybe your site has just been featured in some more popular outlet and there's more publicity for your site, or you're holding some kind of promotion or sales event? So it's not really obvious what is optimal and what is not if you don't have a proper evaluation scheme. And oftentimes, the performance accuracy is not the only criteria, because you need improved model interpretability a lot of the time over accuracy. And you want to optimize for shorter training times, especially if it's an online system that you don't want to run like huge server farms behind because it's unaffordable and might as well use the WAF at that point. So something I mentioned earlier was principal component analysis. Let's say you manage to come up with 1,000 different features from just Apache weblogs, which is pretty common. People have come up with tens of thousands of features based on plain text. And a common statistical method to automatically select features is PCA. So what this does is it helps you to basically run an equation, run a single line of code, and come up with top features that are relevant to your data set that can help you to make your model more efficient. Maybe you select just 2 of those features, and they're able to perform better than using 500 features with 500 different feature weights and biases. So this is just a simple visualization of what PCA does. What it does is it just principal components are the eigenvectors associated with your data set. And when you do PCA, what the algorithm does is it efficiently finds the largest variance within your data and the chosen principal component. So in a 3D space, this means that if you have an axis and you move the axis around your data, it's looking for the principal components, which is this graph right here, is looking for the variance in your data set. So let's say you had an IP address that visits your server 1 time, and then you have another IP address that visits your server 10 million times. So the variance here is 9,999,999. So this is a large variance. And so this is an example of a large variance. And of course, you have to do normalization and regularization, which is just the specifics of which you have to deal with when you're implementing this. But the basic idea is that it's a statistical method that helps you to look for good features. Basically, you want to maximize variance capture, and the idea behind PCA, the hypothesis, is that when you have chosen features that maximize variance capture, then these are basically the most important features. So you want to choose principal components that cover 80 to 90% of the data set's variance. And basically, if you have a curve like this, choosing, let's say, 10 to the order of 0, one feature, and you cover 80 to 90% of your features, then that's a good application of PCA. So how you avoid common pitfalls is to first understand your model well, and then to keep the detection scope narrow. You have to reduce the cost of false positives and negatives, and then you can have hope of having good results from your machine learning anomaly detection. How good is your anomaly detector? How easily can you filter out false positives? This is obviously something that a lot of research has been done on. And I think the most promising one is to always have a human in the loop, which brings you to think of machine learning as a solution in the first place. Because if there's a human in the loop, then the machine learning just basically acts as something to help to filter out the low-hanging fruit, and the human makes all the important decisions. So there's an interesting anecdote here that maybe is true or not, but it illustrates something about using machine learning as a kind of classification engine. So in the 1980s, the Department of Defense purportedly tried to fund a research task for classification of images. So the basic task was to understand if the image contained a tank or cars. So tanks on the left, cars on the right. And if it was a tank, then this engine would basically tell you 0. If it's a car, it'll give you a 1. So during the tests, this model performed very well, maybe 80 to 90% accuracy, which for the 1980s was really good. But when they put it out in the field, they realized that it didn't really work so well. And this is because, like, has anyone heard this before? Do you know why this might be the case? Here. Yes, exactly. So the machine learning algorithm, yeah, that's the right answer. So the machine learning algorithm was actually looking at the raw pixels in the images, and it was learning the entire image and not learning only the focus of the image itself. So when you see the pictures of the tanks, there's lots of sky, there's lots of blue, there's lots of green for grass or trees. And if you look at images on a car, they're mostly photographed on the road. So the raw pixels would mostly contain information about the background and not the object itself. And so when you test it in the field, there are predictions made that may not make sense to a human, because a human wouldn't think about, okay, is this a tank or a car? Look at the background. I wouldn't look at the background at all. I'll just look at the object, because we're so good at object recognition. So this is an interesting anecdote. If you have a machine learning model that learns traffic and you don't really understand what this model has learned, then it's hard to really base your predictions or classifications on this. The next part, I think, is more interesting, how we attack this. So what an attacking a machine learning model is. The first definition is to manipulate the system to permit a specific attack. So let's say I am a malware author. I want to bypass Gmail's malware classification system, which is based on a machine learning model, unsurprisingly. And so what you would do is to slowly feed in data to try to manipulate what the model is learning. Because the Gmail model is learning stuff over time. It is adapting whatever it learns over time to keep up with the latest variations of malware. And so the idea is that slowly doing this, you can start to change what the model is learning and then start to permit some certain things slowly. And you'll be able to get past eventually. The second attack is a more general one, is to degrade the performance of this system. So the problem that I mentioned earlier, which is that sysadmins just get too many alerts and just start ignoring them. So if you can make this happen quickly, then this system will slowly start to lose its integrity. And the term that we use here is called chaff. Chaff is this thing that our airplanes emit out the back of their engines, and this confuses homing missiles. I'm not sure if it still works today, but it used to work in the wartime. So homing missiles would be looking for heat, would be based on image. Smoke would basically confuse it, and they would miss their target because of that. And attacking PCA systems is very similar to the idea of chaff. What you would do is basically to insert a data point into the system and naively assuming that the system accepts all input data points and uses it to adapt to the model. And when you inject chaff, you can move the decision boundary in the direction of your attack. And let's say there was an attacker that has injected enough chaff to expand the decision boundary. let's say in the same example, you run a website and you just started getting a lot more traffic from Russia, and you're just thinking, okay, maybe this is normal because over a period of 2 to 3 months, you see a slow increase in the amount of traffic coming from a particular ASN in Russia, and you're thinking, okay, maybe you just getting more popular in Russia, and then your machine learning obviously doesn't know about the context of which, and using PCA, you'll start to select features that are more salient and will start to accept more of this traffic over time. And there's no clear attack direction, and slowly, when the decision boundary expands, then the attacker will be able to get through. And so obviously you'll think about, okay, if there's a lot of traffic coming in our systems, then doesn't it kind of raise a red flag? That doesn't it alert the sysadmin in the first place? So the idea is that to avoid detection, you go slow. The old anecdote, I'm not sure if it's true or not again, but if you put a frog into a pot of boiling water, it jumps right out. But if you put the frog in cold water and then slowly start to heat it up, it doesn't jump out and it dies. I think I read something that's not actually true, but this is the anecdote, and you understand what I mean. So how you defend against these attacks. These are all proposals in academia, and I'm just taking the gist of the important concepts from all of these papers and presenting them to you. You maintain a calibration set. So let's say you have a test set, and you do cross-validation on your model, and you have a set of points that you detect as outliers on the left. And after the attack, after, let's say, a period of 1 or 2 months, you test your system again, and you realize that this has shifted. And then you realize that, okay, if it's shifted a lot, then maybe someone is trying to attack me. Maybe my traffic has changed a lot compared to maybe the amount of purchase orders I get. I can see if this reflects accurately or not. But then this is a very laborious process, and obviously it's just human manual validation. Decision boundary ratio detection. A lot of the attack methods actually require the attacker to attack around the decision boundary so as not to trigger alerts by humans. Let's say the decision boundary is here and you attack, your attack point lies here. Then obviously you can very simply filter out the points that lie too far outside the decision boundary and not use it to train your model, because you're afraid that using this to train your model might cause a lot of instability in your interpolation. So when you detect a lot of your traffic coming out around your decision boundary compared to when you first had your system, then obviously you can start to look into whether someone is trying to attack your system or not. But again, all these methods have flaws, and they're very laborious. It's not really easy to implement, and if you understand all these things, then you're already a lot better than the average, sysadmin who is implementing machine learning solutions that he's rolling on his own. It's not easy to achieve unsupervised online learning. The thing is to slow adversaries down. I think in any security context, it's the same, and to give yourself time when you're being targeted. So you do this with a bunch of statistical methods like improved PCA, which basically use medians instead of means. You maximize the median instead of your mean, because median is a much more robust criterion for statistical analysis. When you have an outlier that comes into your model, it shifts the median a lot, but not the mean. Find an appropriate distribution that models your data set. A lot of default kernels that are used in scikit-learn are Gaussian kernels or normal distributions, but web traffic is almost never normal. It is more of the time exponential or Laplacian, so you have to think about what your traffic looks like and then model it appropriately. So running my own tests, I just basically look for a large amount of data sets. I didn't have a web server that had huge amounts of traffic, but I found some. And so basically I did PC on it. I'm not sure if it's clear, but this is the cloud of points that I plotted out using PCA on the first dimension, on the first principal component. And using robust PCA, which is the method of using medians instead of means, and also using low rank matrices, the point that the basic trend line that's plotted out is the blue one, and the naive PCA has the green plot. So in the next graph, I injected some attack traffic to try to shift this prediction line. So by the way, this is hard. The problem of adversarial knowledge is important to define, and in most problem cases, the adversary doesn't have knowledge of how your model is implemented. and this is hard. But assuming that your adversary knows when you're training your models and how you're training your models, it is pretty common. There's a pretty common way of doing this, and so it's not a inappropriate assumption. Robust PCA obviously moves less than naive PCA, and you can see that the trend line shifts a lot. And so if you see anything that fits within a certain sigma of those lines, you define them as normal, and outside you define them as abnormal. Naive PCA would have shifted a lot, and that's your decision boundary shifting right there. And I implemented the boiling frog attack, which basically, over a certain number of training periods, tries to avoid detection by going slow and slowing down the rate of attacks, and also messing up the whole system by just throwing random data. And obviously, this also moves the lines. The important piece of thing here is that using naive injection, I was able to avoid detection about 50% of the time. In fact, the numbers are here. So boiling frog injection, which is over 10 training periods, I inject 10% of the attack traffic at each time. I have a 38% evasion success with robust PCA. So even if you follow industry standards, stuff that is recommended by academics, and you use boiling frog attacks, so you avoid detection by sysadmins who are really on your feet, you can get past 38% of the time, which I think is still pretty good. So anomaly detection systems today are not so good, but still improving. Pure machine learning-based anomaly detections are still vulnerable, and using ML to find features is dangerous. But you should always have a human in the loop to understand the features that are being chosen. So what next? I'm going to do more tests on anomaly detection systems that others have created, and to do more research. A bit about myself. I run this meetup group in the Bay Area, data mining for cybersecurity, and it's now about 1,500 people. And if you're ever in the Bay Area, or if you want to join in on our meetups, they're often live streamed on YouTube. So just follow me on Twitter, and then I'll post the link whenever there's going to be a meetup. And this August, I'm going to be speaking at DEF CON on new research that I've been doing in neural networks, and basically releasing a toolkit that will allow you to generate adversarial samples for deep learning systems. So that's it. Thanks. Questions? Okay, no questions. I'll be, oh, there, here. Okay, there's an energy.
Hello, thanks for the interesting presentation. I'm not sure I have well understood how various were the algorithms you tried the data on. I mean, have you tried to play with the various types of algorithms? I know there are many classifiers and stuff.
Yeah, so the algorithm I've chosen for this research is the KNN classifier that was implemented in scikit-learn. So there are studies that do that measure how robust different algorithms are. For example, in decision trees, it's generally more robust than in a logistic regression. And in classifiers, it's generally very dependent on the features that you choose. So because what I was focusing on was actually how PCA was robust, and PCA basically defines the features that you choose. So I chose to go with an algorithm that was very dependent on the features that you choose eventually. Whereas when you're using decision trees, then it's often the model is dependent on a lot of the hyperparameters that you choose. For example, the probabilities that you go down each path, or your refresh rate for the decision tree, or when you're using a logistic regression, just how many dimensions that you have in the first place, I think make the most difference to your model efficacy. So no, I only ran it with KNN classifier. But in the research that I'll be presenting at DEF CON this year, I'm looking at deep neural networks, which is a much larger class of algorithms that have many different kinds of implementations for convolutional neural nets or recurrent neural nets or just Boltzmann systems or autoencoders. So all of these are there's a larger variance there of different algorithms that I've chosen. Yeah.
Hi. Is it working? Okay.
Yeah.
So the set of features that your PCA returns, let's say the top 10 features, is it the same features that an expert would use in the real life without using machine learning, or is it totally different?
Yeah, so it depends on the implementation. PCA doesn't give you the real features. So PCA gives you latent features based on the principal components, which could be close to real features, but then they're not. So typically, when you use PCA, at least in the scikit-learn tutorials, which is like the best practices for how you use PCA, they teach you to, when you run PCA, then you select the top few principal components, the top 5, let's say, and then you would just do a matrix multiplication onto your original data set, and then you'll be able to get latent features that you can use in your data set blindly. So the thing to think about is just that PCA doesn't really know what application it is. It just looks at the statistics. It just looks at min, max, variance, and it tries to give you recommendations on features based on that. But a lot of the time when you're doing machine learning, it's very application specific. So a lot of implementers just use it out of the box. But what I think would make more sense if a human actually understood what constituted those features and then actually chose the features based on the understanding of the content. Anything else? Okay. Thank you.